use the visualizer, and for some of it we'll look at the arguments. So I'll just switch to the visualizer for the first bit. Okay, so isomorphism. So we've been alluding to this topic in what we've done so far. Please do stop me at all if you've got any questions or queries. We've alluded to the idea that at some of the examples of groups we've been looking at, this issue comes up that, well, this group is really perhaps equivalent to that group. Or we've seen, and we'll see more examples now, examples where you've got two groups which are defined and constructed differently, but they look very, very similar. Even to such a point that we start to say, or we might want to say, that maybe we should regard them as being essentially the same group, or sharing all their group theoretic properties. So recall the two groups. One clear example which we saw so this very clearly was when we looked at the groups S3 and D3. Okay. Remember, S3 was all permutations of three objects. All permutations of symbols 1, 2, and 3. D3 was all symmetries of the regular triangle. Now we can list the elements in S3. There's 6 of them in total. There's the identity. There's 3 2 cycles. And then there's 2 3 cycles. Okay, so 6 elements in S3. D3 is 6 elements as well. It was the identity. There was the basic rotation, rotating by 2 turns anti-clockwise, 1/3 of a full turn anti-clockwise. R squared, which would be rotating by 2/3 of a full turn anti-clockwise, say. And then there were 3 reflections, and if we named one of them, remember when we looked at this, we named one of the reflections. The other reflections can be expressed as R after S and R squared after S. If you compose any particular reflection with the rotation, you get another of the reflections. And if you compose it with the other rotation, R squared after S, you'll get the 3rd reflection. So these two groups both have 6 elements, and in particular, they kind of seem to come together when we took our, but at this stage, at the beginning, although they both got 6 elements, they're both very different things. S3 is this group consisting of rearrangements of 3 objects. So it's not even a geometric thing. These rearrangements of 3 objects, they aren't taking place in the plane or in some geometric space. They're just taking place in this discrete space consisting of 3 separate labels, 1, 2, and 3. Whereas D3 consists of quite different types of objects. Each of these objects here in D3 is a function from R2 to R2. It moves the triangle around in such a way that it's still the same triangle, but it also moves all the other points in R2 around. So they're very different objects, okay? Apples and pears, right? These are permutations of 3 distinct labels. These are transformations of the plane. But once we get to this picture where we take our triangle and we come up with this natural idea of labeling the vertices, then suddenly the distinction between the two starts to kind of melt away, and the two kind of become, surely these are the same group, okay? Because if we label the vertices starting off, then each of these each of these elements of D3 becomes naturally associated with a permutation of the three labels, okay? Because R seems to be the same as, well, if you rotate it by 1/3 of a full turn anti-clockwise, the thing at position 1 is going to go to position 3. And the thing at position 3 is going to go to position 2. And the thing at position 2 is going to move to position 1. So R squared will be the other three cycles. If that's the axis of our one signified reflection S, then S is very naturally associated with the permutation, the transposition through 2. You perform S, when you reflect the triangle like this, it interchanges 2 and 3, but not the other ones. And similarly for the other two reflections, RS and R squared after S. Okay. So we see, see this natural thing that really the things going on in this group seem to be exactly the same as the things going on in that group as well. Okay. So these two groups, S3 and D3, seem very similar. And maybe ought to be regarded as equivalent. Maybe if we want to embark on some grand exercise to describe all the groups that there are, you know, maybe we should have these in the same category. Maybe we should even regard them as essentially the same group. Okay? Well, this way of talking, which is a very natural thing to do, this is made precise and rigorous with the concept of isomorphism. Okay, so let's look at the formal definition now, and then we'll look through some more examples and see it used in various ways. Okay, so the definition. So this is basically just going to take this straight from the notes. So you've got two groups. Now, normally up to now, we've been omitting the group symbol, the group operation symbol. We've been writing all our groups multiplicatively. But for this purpose now, we're going to reintroduce them. So what he uses a dot for G and circle for H. So remember, the group is the set and the certain operation defined on the set. So here, when we're introducing this definition, we're just using these two abstract symbols, a dot and a circle, to represent. So the dot is the operation that's taking place in the group G, the circle is the operation that's taking place in the group H. Okay. Now, it's quite a similar, I mean, you'd almost say it's the same operation taking place in S3 and D3. It's composition of functions. But we're going to be meeting cases where, like, the operations in the two groups are certainly very different. Sometimes it'll be composition of functions in one, and maybe addition of something in another one, or so. This emphasizes that there's no requirement that the operations be the same operation. In general, they'll be different because they're different operations defined on different sets. Okay? So these two groups are isomorphic. So isomorphic is just a technical term that we use for this, but you should think of it as being equivalent as groups. But what we mean exactly, if there exists a bijection, so there must exist a function between the two groups. Okay, we'll just say that phi is going from G to H, but there's no, this definition is a symmetric definition. We'll see very clearly. If G is isomorphic to H, then it's also true that H is isomorphic to G. It's really an equivalence between the two groups. So we must have a bijection between the groups. Remember, what's bijection? A bijection is the nicest kind of function between two sets you can have. It's a one-to-one and onto function. So in particular for finite sets, that means the two sets have to have exactly the same number of elements, okay? Because if you want to have a bijection from a 6-element set like S3, the codomain of it has to have 6 elements as well. So it's going to be a one-to-one and onto function. So each of these elements we're asking to map it to a separate distinct elements from all the other images. So the 6 elements in your domain, there must be 6 in the codomain. So if there exists a bijection phi, but now not just any old map between the sets. This is what I've spent some time commenting on in the reading notes. This function has to have a very particular property. What we want it to be is, we want this function to, there's different ways of saying it. One way of saying it is, we want it to respect the group structure in the two groups. We want it to fit well with the group structure in both groups. We want it to honor the group structure. Or some people say we wanted to preserve the group structure. Now, what does that mean? It means that whatever phi is doing to the elements of G, it's mapping them to elements of H, but it must do so in a way that perfectly aligns with the group operation. Okay. So what that comes down to is this condition. For every pair of elements in the set G, if you look at phi applied to the product x times y, now see x and y are from the group G, so the product x times y is just some other element of G. Okay, so if phi is a bijection, phi is going to send that product to some element of H. But we don't want it to be any old element of H. We want it to be the product of the two images, phi of x and phi of y. But of course, the group operation taking place here, is circle. Because this operation is taking place between phi of x and phi of y. Well, phi of x and phi of y are elements of H. So they're combined using the group operation circle. Whereas this product here, x times y, x and y are elements of G, so those are combined using the group operation dot G. So if there exists such a map satisfying that, then we say the two groups are isomorphic, and we write, the notation that we write is that G, we wouldn't want to say that G is equal to H, okay? Although we sometimes might say that in an informal way, or sometimes we might say they are the same group, but strictly speaking, we want to avoid saying that. I certainly wouldn't want to say that S3 equals D3, because this contains transformations of the plane, this contains rearrangements of 3 objects. There's certainly a strong link between them, but I wouldn't want to say G is equal to H. So we have this annotated equals sign with a tilde on top of the equals. That's what we write when they're isomorphic, and if you're reading this out in English, you say G is isomorphic. G is isomorphic. Okay. And we should regard this as being the correct way of saying that phi respects the group operation. Okay. It would not be respecting or honoring the group structure of G if it sent the product x times y to some element that was different to this. Okay. Let's immediately jump into another example, which is example 9.1. Let's see this book. We'll take this example, and then maybe we'll just look at a couple of other ones from his notes. So this is another example of 2 isomorphic groups. So consider I as an element of the complex numbers, the non-zero complex numbers under multiplication. So this is the group of non-zero complex numbers under multiplication. And what this is saying that if you look at the group generated by I, the subgroup generated by I, that this is isomorphic to the integers modulo 4 under addition. Okay, this is a good example here. Now, this can be readily seen, or this can be appreciated from their Cayley tables. It's a good way to see this. We look at the Cayley table of the group of integers modulo 4 under addition. This is addition modulo 4, quite a simple structure. You add 0 to something, it doesn't change it. You add 1 to something, increases it by 1 modulo 4. You add 2 to something, it increases it by 2 modulo 4. You add 3 to something, it increases it by 3 modulo 4. Okay. So from this, so it's a 4-element group, so there's 16 entries in the table. And there you can see everything going on in that group. If you look at the subgroup generated by I, this is set 4 plus, here's the subgroup generated by I. Well, what elements are in this subgroup? Well, certainly the identity, which is 1. Remember, the group operation here is multiplication. I, you've got I squared. The better name for I squared is complex numbers.
-1.
-1 might be a better name for it. And I cubed, well, maybe a better name for I cubed is a simpler name. Minus I, isn't it? For your unit circle in the complex plane, got 1 I minus 1 minus I. It's 4 points around the unit circle. These are the fourth roots of 1. Take any of these numbers and raise it to the power of 4, you're going to get 1. These are our elements here. Everybody multiplies something by 1, you don't change it. You multiply something by I, change that to I squared is -1. Minus I, and gives you minus I squared, which is +1 again. And changing the sign of everything. And lastly, multiplying by minus I, is 1, gives you I, and minus I gives you I squared, which is just -1. So they're clearly very different group. They're clearly different groups. The objects in them are different. Here are the congruence classes of integers, modulo 4. Here are 4 different complex numbers. So they're certainly, you wouldn't want to call them the same group. But from looking at their Cayley tables, we see they both have exactly the same structure. There's 4 elements in each of them. Of course, when you make the identity, the first element in the group, the top row of the interior of the Cayley table is always just the same elements, the same column headings just written out again. Yeah. And you see the structure here, because it's a cyclic group generated by 1, the structure here is that each next row is just the previous row slid 1 position to the left and wrapped around. Yeah. So the 1 slides to here, the 2 slides to here, the 3 slides to here, and the 0 slides to there. And the same thing happens for getting to the next row and the next row. That's the pattern. That's what's going on in that table. But look here, it's exactly the same. Okay, we've got the identity as the first element. So the top row is just repeating the column headings. But then the next row is everything just slid 1 position to the left. and wrapped around. And similarly for getting the third row and the fourth row. Okay. So the key observation here is these Cayley tables are really the same or equivalent. They both have exactly the same structure. After an appropriate relabeling, they are exactly the same. Now, what is this relabeling? Really, well, we want to relabel. So if we start with this one here, how do we relabel this Cayley table, the one for Z4? How do we relabel it so it becomes the Cayley table for the subgroup generated by I? Well, we have to agree, instead of 0, we're going to write the letter 1. Maybe don't take this down, I'm leaving some spaces in the add to what I'm showing here. Instead of the number 1 in Z4, we want to say that we're going to relabel that as I. And instead of the number 2 in Z4, we're going to relabel that as -1. And instead of the number 3, we're going to relabel that as -I. Now, what is this relabeling? This relabeling is a way of pairing up an element from Z4 with an element from the subgroup generated by I. In other words, this relabeling is our bijection. This is the phi. This is the function, the map between the two groups. So we're saying phi of 0 is 1, phi of 1 is I, phi of 2 is -1, phi of 3 is -I. Okay? So phi, this is our mapping phi, which sends Z4 plus 2 the subgroup generated by I. Okay, it's clearly a bijection between the two 4-element sets. Each element is sent to a distinct, unique element image from all the others. The observation that and I'll put it in quotes, the interior of the tables are the same after relabeling. That observation is equivalent to, that really is the statement of the isomorphic condition. Just write both of them multiplicative. Okay, because when we say that after relabeling, the interior of the tables looks exactly the same. For instance, this 3 here in this position. Well, under the relabeling, we say phi of 3 is -I, and yeah, we do indeed see a -I over there. So the relabelings the relabeling that we've done on the elements also carries the interior of the tables over. But then we can see that this is exactly this condition here, because when I say this 3 here, well, this 3 is the product of 2 and 1 in this group, okay? So we can consider, so for example, we could have our x is 2 and our y is 1. If x is 2 and y is 1, x times y in this group, I know it's addition, but just speaking generally, x times y in this group is this element here in the Cayley table 3. So what I'm asking that is that when you do phi of that it's the same as the product phi of x and phi of y. Well, phi of x, you see, we agreed to call phi of 2 -1. So phi of x is this position here. Phi of 1, we agreed to send 1 to I. Phi of 1, that's phi of y, is this I up here. And indeed, the product 5x times 5y in this group is indeed minus I, which is the same thing as 5, 3. 5, 3 that we did, okay? So that shows you that, that observation, and like when we were looking at the triangle before, when you see this way to kind of call, to relabel or associate all the elements of one group with the elements of another one, in a way that seems to be respecting the group structure or mirroring the group structure. Or in other words, and another way to state that is you see a way to relabel one Cayley table so it becomes the Cayley table of the other group. That really boils down to having a bijection phi satisfying this condition. So it makes it much more concrete and formal. So now, instead of talking about, there's a way to associate the elements or you can relabel the elements, well, we've got that defined very carefully, is that there must exist a bijection between the two sets. And then saying that it relabels the Cayley table into the other one, or there's the same group things going on in one group to the other. We've now boiled that down to this very straightforward, clear, rigorous condition. That phi of a product x y is always the same as phi of x times phi of y. Any questions just on that? Kind of initial run through the definition and looking at our first example. Now what I've said, I've made some comments in the reading notes. This condition here, you see here in green, this is sometimes called the homomorphism property. Not the isomorphism property, the homomorphism property. Okay, what's a homomorphism? Well, a homomorphism is a map between two groups which satisfies this, but isn't necessarily a bijection. Okay, so it's more general still. Some books, and this is what I've said in the commentary, some books or authors would instead define a homomorphism first. That's the larger class of objects. Homomorphisms are mappings from one group to another one that respect the group structure. But they don't necessarily say that one group is equivalent to another one, because we don't have this condition that it must be a bijection. But it's just some map from one group to another one that respects the group structure, that has this homomorphism property. And then after talking about homomorphisms in general, you then meet the concept of isomorphisms as a special class of homomorphisms. They're the homomorphisms that are biject. This book, Judson presents it the other way around, where we meet isomorphisms first. And I think that's a better way to meet it, because we've already seen this and felt this in some of the examples that we've been looking at. These groups, these two distinct groups, really ought to be regarded as the same. So we've kind of already met the concept. So it's good to see that, and because it's a smaller class of things, it's easier to understand perhaps than the wider, more general class of homomorphisms. But in a couple of chapters' time, we'll be considering maps phi, which aren't necessarily bijections, but which satisfy this property. So it's a much larger class of maps. So the requirement that phi be a bijection is quite strong. Okay. So let's have a glance at a couple of his other examples. I won't necessarily talk to them myself, so let's just look at his textbook. So example 9.2 is an isomorphism from, so this is kind of interesting, from the additive group of real numbers. So you consider all the real numbers under the operation of addition. So that's a group, certainly. That is isomorphic to real numbers under multiplication, but just the positive real numbers under multiplication. Okay? And the map that gives it to you is the exponential map. Okay? Sending x to e of x, e to the power of x. The reason it's an isomorphism, well, it's certainly a bijection. The fact that it's a bijection comes from properties of the exponential. It's 1 to 1 and 1 to 2. You can kind of appreciate that when you think about what
think about what the graph of the exponential function is. The graph of the exponential function looks something like this. So this is the real numbers here. It's asymptotically tending to the x-axis as you get larger and larger in the negative direction, and it's increasing without any upper bound as you go in the positive x direction. And the reason it's so, it certainly covers the whole of the positive real numbers. So you can get arbitrarily close to 0 by taking a large negative argument, and you can get any real number at all. If you just go far enough out along here, eventually you'll reach a certain height because it's unbounded. The fact it's one-to-one comes from the fact that it's strictly increasing. The function's strictly increasing, so any horizontal line here cuts the graph in exactly one position. Okay? So any object here is only ever the image of a single element, of a single argument. So that's kind of, properties of the exponential function mean it's a bijection. And from our other knowledge of the behavior of exponents, we see that the isomorphism or the homomorphism property is satisfied as well. If you take the exponential of a sum of two numbers, well, you're familiar with properties of exponents. You can write that as e to the x times e to the y. But then you're taking these two numbers, e to the x and e to the y, and multiplying them. So in other words, you're multiplying 5x and 5y. So it's very natural that the homomorphism property is satisfied when you go from an additive group, taking exponents, into a multiplicative group. Okay? Because when you multiply powers, you just add the exponents. That's basically the one there. Something very similar is shown in the next example, where you go from an isomorphism from the integers under addition, to the subgroup of non-zero rational numbers consisting of all the powers of 2. So this is really the same. This is really the same idea as the previous example. Instead of using the number e, we're using 2 as the base. Yeah. So we only ever get powers of 2 or powers of a half. So we get rational numbers, and we're just using the integers as the domain. But again, this key property, when you multiply powers, you're adding the exponents. That provides the homomorphism property. Examples which are maybe not so immediately obvious is, so let's say U8 and U12. So U8 and U12, these are the multiplicative modular groups, modulo 8 and 12. Remember, this was we would have called it Z8 cross multiplicative groups, Z8 and the multiplicative group Z12 in our number theory studies last year. But when you look at their Cayley tables, so 1, 3, 5, 7, 1, 3, 5, 7. When you look at U8 over here, and U12 over here, which is 1, 5, 7, 11, 1, 5, 7, 11, 3. Yeah, so I've written out the same elements in the same order. When we do this relabeling, take the Cayley table of U8, relabel the elements like this, so that they just go to the same elements there in the same positions. That transfers the Cayley table of one to the other. For instance, when you look at 5 squared, 5 times 5 in the group U8, well, 5 by 5 is 25. With modulo 8, that's equivalent to 1. Because 25 is congruent to 1 modulo 8. So 5 by 5 is 1. Well, if 5 is going to 7, if we see 5 squared as 1 here, well, if 5 gets mapped to 7, then 7 by 7, that should give us 1 here as well, okay? Because we're mapping 1 to 1. 1 is the identity of both groups. 7 by 7 is 49, and here we're looking at modulo 12, and of course 49 is 48 plus 1, so that's congruent to 1 modulo 12 as well.
If you look at all the other entries, you'll see, again, the homomorphism property is satisfied. The elements in the interior of the table of U8 do indeed get transferred by this map between them, this map phi, to the appropriate element over in U12 with respect to the group population. Okay, so example 9.5 is an interesting one. This is our first negative example. Well, we can already easily generate lots of negative examples, i.e. examples of pairs of groups that are not isomorphic, because we've already seen that the mapping phi has to be a bijection. So for finite sets, that means they must contain exactly the same number of elements. So if you can construct, show a pair of groups that have different numbers of elements, they cannot be isomorphic, okay? Because there can't be any bijection between them if they've got different numbers of elements. But perhaps more interestingly is seeing an example of a pair of groups that do have the same number of elements, which are nonetheless not isomorphic. So the example they're using is S3, groupfold permutations of 3 elements, with 6 elements in that, 3 factorial, and the group Z6, the additive group of integers modulo 6. They're both of size 6, so there are bijections between them. Okay? You can just write down the 6 elements of S3 in some order, and then just count them off 0, 1, 2, 3, 4, 5. That'll be a bijection from S3 to Z6. And there are lots of those bijections. There are probably 6 factorial number of those, because the first one can be sent to 6 elements to keep it a bijection. The second one must be sent to one of the other 5. Yeah, so I think there's 6 factorial, which is a huge number. 6 factorial, it's quite large. It's a huge number of bijections. But what we're going to show here is none of them can possibly be an isomorphism. None of them can possibly have that homomorphism property. And that says the 2 groups, there's no way to make the 2 groups look the same. There's no way to take the Cayley table of S3 and relabel it so that it looks like the Cayley table of Z6. Now, how can you possibly do that? Because there's 6 factorial different bijections. It's a lot of bijections. Well, we do it using, we certainly don't consider each one case by case basis. I mean, you could look at all 6 factorial possible bijections, and in each of them note that it doesn't transfer the Cayley table of S3 to the Cayley table of Z6. Okay, that'd be extremely laborious and not very informative. Really, we can prove this, and it comes down to the commutative nature of the operations in both cases. Okay. So in S3 is an example of a non-abelian group. Okay, because when you take pairs of elements, to 2 non-identity elements here, multiply them together, it makes a difference in what order you do them. Okay, you always get a different answer if you take 2 different non-identity elements from S3. Whereas the integers under addition modulo 6, they are commutative. So we can do this as a proof by contradiction. So we suppose one of these bijections was an isomorphism. So suppose we have phi, which is an isomorphism. Then if you consider, take a pair of elements A and B, which show the non-commutative nature of S3, the non-abelian nature of S3. So 2 elements A and B, such when you multiply them, you get different answers. Well, if phi is an isomorphism, well, phi is a bijection, so we suppose we have, so it's going from Z6 to S3. So let M be the pre-image of A, and let N be the pre-image of B. And then we see what the consequence of the homomorphism property is. Now, the homomorphism property is this property here, that phi of M plus N is equal to phi of M times phi of M, or phi of M after phi of N, because that's the group, the group operation in S3 is composition of mappings. So phi of M after phi of N is written AB. But of course, the operation, the group Z6 is commutative. M plus N, M and N are 2 integers modulo Z modulo 6. M plus N is the same as N plus N. So certainly phi of M plus N has to be the same as phi of M, N plus M, because these elements are both the same, m plus n or n plus n. But when you apply the homomorphism property here, you see this is equal to 5n after 5m, which is equal to b after a, b times a, b plus 3. So you see you're forced to the conclusion that a, b does indeed equal all the way through ba. But that contradicts our choice of a and b. A and b were two of the elements of S3 that show the non-commutative property. So that's a contradiction. Where did the contradiction come from? The contradiction came from assuming that there was an isomorphism between them. Okay. So these two groups should not be regarded as being essentially the same. We would rather call them they are very different groups. Even though they've got the same number of elements, quite different. One is abelian, the other one isn't. Okay, any questions? Okay, we've taken our time with that. We've really just looked at the definition of isomorphism and looked at some of these key examples and initial examples. I won't blast through. I was hoping to get through Theorem 9.6, but I won't blast through that. So on Thursday, started this whole section a week early. If you look at the schedule on Moodle, I did have this week as cosets and just here and again. So I started this a week early because I realized it's going to take a bit more time before probably mapped out for the next 3 weeks or so. But this is good. So on Friday, we'll go through the rest of the isomorphism material here. But I'd encourage you to read it in the meantime. There's some of the proofs, there's gaps, and where he leaves them as exercises. So we'll discuss those in class. And we'll also meet the two product constructions, external and internal direct products, and we'll have a go through the exercises as well. Okay. Finish on time for once.